It's a pleasure to introduce Roberta Iseppi, who will speak on the BV formalism in non-commutative geometry.
Thanks a lot for the introduction. So let me start by thanking the organizer of this workshop for inviting me and for giving me the possibility of telling you something about the problems I've been working. As written in the title, it's going to be a brief overview. So I will try to keep this promise of being brief. But if any of you, of course, has questions and wants more details, I'm happy to give all the details and calculations and whatever is needed. But as I said, let's start by telling what is the setting. So the main character of this story is the concept of a gauge theory. So here, for me, a gauge theory is something very simple. So somehow I'm reducing the concept to its essence. We have a configuration space that I'm going to denote by x0. And there is then an action functional here at 0, defined over a configuration space and taking values in R. And then I'm supposing that there is a gauge group acting on the configuration space and leaving the action unchanged. Okay, so more or less what I'm describing to you is just a physical theory with some kind of symmetry. So the problem is that when we have these symmetries, so mathematical symmetries, but not like physical symmetries, problems appear when we try to quantize them. So this is the context where the BV formalism was first developed. So try to consider to compute the path integral or the partition function, sorry, it's more complicated than what I thought. So it's here, a partition function of your theory. So you have an integral, so a configuration space of an expression containing your action functional. So as we know, this kind of path integral not well defined for many, many reasons. But a possibility for dealing with that is just say, okay, if I'm sending my parameter age to 0, I just apply some stationary phase formula. So my not well-defined object, because for example, there is not a well-defined measure, I just see them as an expression, as a sum taking over the critical points of my action functional. So in this kind of expression is where often you get these Feynman diagrams appearing. Okay, but what happens if I have a gauge theory? So the idea is that I can apply these formulas when my critical points are isolated. If I'm dealing with a gauge theory, of course, critical points appears in orbit. How can we solve the problem? So of course, we want to solve a problem in a way that is not changing what we want to compute. So one might think, okay, just why don't quotient? So all the points on my orbit are defining some kind of situation that from a physical point of view is absolutely the same. So just quotient by the symmetry. But often this is not really nice from a mathematical perspective. So a solution can be to go to the opposite side of the spectrum. So instead of quotienting, let's add stuff. So the idea at the base of the BV formalism is that we are adding auxiliary variables. So we are adding them, and they are called fancy as ghost fields. So the ghost fields are nothing more than, as I said, auxiliary variable characterized by two objects. So the ghost degree is an integer, and their parity, which can be real, 0, or Grassmannian, 1. Of course, as you want intuitively, the parity of the degree coincides with the parity of the variable. And actually, what distinguishes the BV formalism from others, so let's say the Pavet Popov ghost or the BRST, is that actually we are imposing some kind of duality. So namely, for each ghost field, we are also introducing what we call the anti-ghost. So it's just somehow a dual variable, so with the ghost degree of the anti-fields that is minus the ghost degree of the fields, -1, and opposite parity. Of course, I'm telling you a story that actually is more complicated. So this is just a picture of trying to describe what is a BV formalism. So from a mathematical perspective, you can describe it very differently depending on what is the language, the mathematical language you describe and you use. And of course, this is just a picture. It's not complete. And I apologize with all the people that actually are not appearing here. But yeah, so somehow to give you the idea of what is this BV construction. So it's a sequence of steps where the one that I'm describing you somehow is just the first one. So this idea of introducing new variable and new ghost. As you can see, the bottom line is made out of complex, cohomology complex. And this is why some people like to describe the BV formalism as a cohomological approach to gauge theories. So for example, for the first one, as you can see, so what I'm doing somehow, I'm adding ghosts, and the new pair I'm obtaining somehow naturally define a cohomology group. And it would be interesting to tell you, for example, the intercept of this cohomology, because they actually capture some physical property of your model. But as you see, there are a few steps, and why are they there? Because actually they allow you to solve the problem. So remember that we wanted to deal with an expression like that, some kind of integral on the configuration space of an expression involving our initial action. So the idea at the base of this BV formalism is that one can prove that the integral you were interested in actually doesn't really depend on the space where you're integrating, but it depends more on the homotopy class of the space where you're integrating. And also for the action as 0 appearing there, I mean, of course, your integral depends on that, but not really on the function itself, but on the cohomology class, on this quantum BV cohomology class, where your S0 is a representative. So then the idea is simple. So why we don't just search for better representative? So instead of taking my configuration space, initial configuration space, where I'm not really able to integrate, I deform it to a new sub-Lagrangian manifold. And similarly, I'm not taking my S0, but I'm taking another representative. So I'm adding some small deformations, some more small correction, staying in the same cohomology class. And I tune these two parameters, so my sub-Lagrangian and my new action, in such a way that then I found an action functional with isolated critical points. And then I know how to solve this. I just apply the stationary phase approximation. So the BV formalism is what tells you how to tune these two parameters to find a new sub-Lagrangian where your action functional has isolated critical points. So that's somehow the essence. Here I was hoping to tell you a little bit what can be the math on that. So this is one of the possible approaches. Here is the setting of gauge theories over an affine configuration space. So your configuration space is just a affine space, and your function is an element in the structural ring of your affine variety. And as a symmetry, we are taking UN. So by adding those, what I want to obtain is a new configuration space, supergraded vector space, that satisfies two conditions. So the first one, for example, is what I was telling you. So we are imposing this duality. For each ghost, we have a corresponding anti-ghost. The second condition is something natural. So we don't want to change our initial theory. So if we do restrict to degree 0, we want to go back to what we had. So the part of degree 0 and this degraded supervector space is just your initial configuration space, and similarly for the action. The third condition is for this new S tilde, so it's a regular function, this time involving ghost, anti-ghost, as these extra terms. We ask that is a solution of the classical master equation. So one as like a natural, doesn't really work. It's more complicated, sorry. There is a natural 1 degree Poisson structure coming from pairing of an anti-field with corresponding fields. And so this is just the classical Poisson structure. We impose that that S tilde is a solution of the classical master equation, and this is what tells you that there is a natural cohomology in this. So, and this is of course related to the symmetry of the action. But okay, where non-commutative geometry comes in the picture. So as I told you, my idea of gauge theory is like really reduced to the basics, because for many people, when you speak about gauge theory, you're speaking about principal bundles. But when you consider spectral triples, so you have your algebra, your Hilbert space, your operator D, one can actually think about inducing gauge theory in this more like generalized meaning. So we all know that when we are given our algebra, we can consider our algebra in a spectral triple over that. We can consider a new algebra B, which is Morita equivalent to the first one, and somehow transfer the structure of spectral triple from A to B and construct a new one. Of course, one can do this kind of mechanism on an algebra itself, so self-Morita equivalent. And then one can see that actually transferring the structure to the new algebra, which is actually the same algebra, doesn't change the algebra, doesn't change H, but change the operator D. And so here you see the right candidate for speaking about a gauge field in this setting. So just an element that can be written as a sum of products of an element in the algebra, this A, J, and a commutator of T with another element, with the extra condition of being self-adjoint, where the star is a star on the algebra. Okay, so of course, somehow with the spectral triple, we have the space, we need the action. And the right candidate for that is just considering the spectral action. So here I'm just recalling the definition. But this is telling you that each time you're given a spectral triple, there is a natural way of defining a gauge theory in this kind of generalized meaning. So the gauge field are the inner fluctuations, the action is a spectral action, and the gauge group is given by the unitary element of the algebra. Then, of course, the question now comes naturally. We have a spectral triple, it induces a gauge theory. What about the BV construction? So we are given our gauge theory, we try to apply the BV construction. Can this be described in terms of spectral triples? So what I'm trying to formulate, explain, is that one would like to really complete this kind of diagram. So we start with our initial spectral triple. You can construct the induced gauge theory and then apply the BV construction. As you might notice, actually, I'm starting with a finite spectral triple. So finite spectral triple are finite algebras, so matrix algebras, and induced gauge theory is an affine gauge theory. So the configuration space is an affine configuration space. And as you might remember, so from that diagram, or that picture of how the BV formalism look like, we do have a method to perform the BV formalism over affine gauge theories. So we have a way to perform this construction. It's not so easy, but it's doable. Can we lift it to the world of non-commutative geometry? And what I'm telling you is just how it works a little bit the first step, so how you can perform the first extension, so introducing the ghost and the anti-ghost. So somehow what is the construction telling you is that, first of all, you have to move to a real spectral triple. And this is needed because somehow spectral triple are naturally defined over complex, but when you want to speak about physics, you actually need to go back to real. And so the algebra turns out to not play a central role. What is more important is actually the Hilbert space. So remember, we want to construct a spectral triple that encodes this ghost and ghost for ghost, this extra term we introduce, and they do appear inside the Hilbert space. Yeah, I'm just showing you how it looked like for a very tiny model. And then the operator D, the new self-adjoint operator for the new BV spectral triple, is what contains these extra correction terms in your action functional. And as I said, the J is what is needed to go back to real fields. So somehow schematically, this is a comparison how you go from your initial spectral triple to the induced gauge theory. So the fields were coming from the algebra, and the action was just the spectral action of your spectral triple. While for BV spectral triples, you see that what plays the role is the Hilbert space that contains the ghost, and your BV action counts as fermionic action of this new spectral triple. And here is just for telling you that one can actually complete the diagram and find indeed all the other steps, and it completes also nicely for the cohomology. So this is a way somehow to lift the construction at the level of spectral triples. So of course, question comes, what is next? So that's what I presented you was the case of finite spectral triples. Of course, interesting question comes when one go to proper spectral triples. So these are just a few open problems I'm currently working on. So you might recognize here something similar what previous speakers were speaking about. Of course, for me, this is the BV formalism for fuzzy geometries. So physicists like to call it towards quantum gravity, but it's a matter of taste. But yeah, so this is just for saying that interesting result has been achieved, and many more interesting questions are now there to be answered. But thanks for your attention.